Welcome. In this session, we'll look at a couple of examples of use of multivariable chain rule. So the multivariable chain rule is used when you have functions of several variables and you compose such functions in some sense. So substitute functions of several variables in functions of other variables. Let's take a simple example first where we have just one final variable. So here w is a function of x, y, and z. X, y, and z are themselves functions of t. We'll use the chain rule to find the derivative of w with respect to t. First, we write down the chain rule for this situation. So remember how to do this from our last session. For each intermediate variable, we write down the chain rule as if it's a one variable case. So I take dw over dx times dx over dt. This is the chain rule if x was the only intermediate variable, the old one variable case. Because w is a function of x, y, and z, we get a contribution from x. We also get a contribution from y of the same type, dw over dy times dy over dt, and one from z, dw over dz times dc over dt. Now we calculate each one of these. For w, the derivative with respect to x, first I differentiate for ln. That gives me the reciprocal of what's inside ln, namely x squared plus y squared plus z squared in the denominator, times the derivative of this what's inside ln with respect to x. That will be 2x from x squared, and since we treat y and z as if they are constant, we get 0. So altogether I get 2x over x squared plus y squared plus z squared. I should multiply this by derivative of x with respect to t. X is 2 minus 3t, the derivative is just negative 3. Now we do the same thing for y. dw over dy is just like dw over dx. First differentiate for ln, then differentiate the inside. This time I get 2y for that. And then find dy over dt, which is 2t. And finally z, where we get 2z over x squared plus y squared plus z squared for dw over dz, and negative 1 for dz over dt. If we want to write it purely in terms of t, we should substitute for x, y, and z. And if I had substituted for x, y, and z in w first, I would have gotten this. And if we differentiate this as we did in chapter 12, we can verify that this would be the answer. So in a sense, the multivariable chain rule is not really necessary for calculation, because when we do partial derivatives using techniques of chapter 11 and 12, this is kind of built into that. In some sense, multivariable chain rule is equivalent to the rules of differentiation we saw in chapters 11 and 12, or several of them. We can do the same thing when you have partial derivatives. So now let's take a case where I have a function of x and y are themselves functions of r and s. As with the one variable chain rule, if you want to evaluate the partial derivative, you can do that as you go along. I'll show you by an example how that works. So again, we'll do this using the chain rule rather than substituting first. So we need to write down the chain rule for dz over dr. Now I have two intermediate variables x and y. So I write down the contribution from x first, which is dz over dx times dx over dr. And then the contribution from y, dz over dy times dy over dr. And that's all that is. So we just add those two. And now we calculate these partial derivatives. Z is 5x plus 2y raised to the power 1/2. So I use the power rule. First differentiate for the exponent 1/2. So I get 1/2, and then 5x plus 2y to the power 1/2 minus 1, which is negative 1/2. Then differentiate what's inside. That's 5x plus 2y, its derivative with respect to x is 5. Then we do dx over dr. So differentiate this with respect to r, which gives me just 1. Now we repeat this for the second term but with y. So the partial derivative of z with respect to y will be, again, the power rule first, 1/2 5x plus 2y to the power negative 1/2 times derivative of 5x plus 2y with respect to y, which is 2, times derivative of y with respect to r, which will be negative 3. Okay. So you don't really need to simplify it. I'll just simplify it a little bit by doing the arithmetical multiplications. Now we are going to substitute s equals 1 and r equals negative 1. But since my answer at this step is in terms of x and y as well, I need to find their values first. X is 4s plus r, which will be 3, and y is 2s minus 3r, which will be 5. So we plug in 3 for x, 5 for y, 1 for s, negative 1 for r, the expression we have for dz over dr. That gives me the value of dz over dr when x equals 1 and r equals negative 1. Of course, you can simplify this and verify that you get 1/10. So this is a rough idea. We should just give you a rough idea of how to use the chain rule for multivariable situation if the need arises. I will stop here. Goodbye for now.